Hello everyone, welcome back. This is Monica Lupion, the instructor of the course CE318 Heat and Mass Transfer. Today I'm going to go over one example of 1D dimension, the steady state conduction from the recitation class. Just to refresh in memory, we already mentioned about the methodology suggested to solve the problems. First, read the problem through carefully, especially in quizzes and exam, till the very end, because sometimes at the bottom there is an important note for the solution of the problem. It could be either a simplification or an assumption that we should take. Then my recommendation is to draw a diagram with the main elements of the problem, so you have a clear idea about the information that is provided, about the parameter that you need to calculate. If there is some specific information about the geometry, for example, write down the equations. Do not forget to write down the equations, because if you do a mistake, if you make a mistake during the calculations, I'm gonna put more emphasis in the equations than in the calculations. Then do the calculations considering units. Do not forget, sometimes you have to convert to units. If not, well, it's not only that you won't get 100% of the points, but also since you have to use sometimes these values to get into a diagram, well, if you make a mistake, then the diagram will be also wrong, and it's like a cascade effect. And finally, please box the solution. So what is the example that I want to discuss with you today? Well, this is a recitation about one-dimensional steady state conduction. So this is an example of one-dimensional steady state conduction. That means that there is no dependence with time. That is the meaning of a steady state. It's one dimension, so we will only focus on one dimension. We don't worry about having 2 or 3 dimensions. Is conduction. Okay, so let me go through the problem with you, and then I'm gonna solve it. So we have water and air flows separated by a square steel plate wall with a length of 1 meter and a thickness of 3 millimeters. To increase the heat transfer rate between these fluids, Mr. John Cool decided to add straight rectangular fins of 1.25 millimeter thickness and 2.5 centimeters length, spaced 2.0 centimeters apart. The steel has a thermal conductivity of 45.1 watt-meter Kelvin. The air side and the water side heat transfer coefficients might be assumed constant with values of 15 and 250 watts square meter Kelvin respectively. Please calculate the percent change in the total heat transfer when feet are added on air side. Well, so as always, I would like you to try to solve this problem first by your own, and then you can compare with the solution that I'm about to solve, okay? But just to go over like an overview of the problem. So we have water and air separated by a steel plain wall with certain dimensions, and we need to calculate the percentage change when we add fins compared to the case when we don't have fins. So what we're going to have to do here is to calculate heat per area when there is no fin, and then heat per area when there is fin, and compare these two values. Okay, let's go for it.